Hello everyone. So today I'm going to present my work on a simplified framework for Zeroshot Cross-Modal sketch data retrieval. This work is brought to you by IIT Bombay from Center of Studies in Resource Engineering by me Ushashi Chaudhary, my colleagues Biplab Banerjee, Avid Bhattacharya and Mihai Datko. So before we begin with, what is a Zeroshot Learning? So a Zeroshot Learning basically aims to solve a task at hand without receiving any example of that at the training phase. So basically here in this problem we want to do a sketch-based image retrieval problem wherein we have images as well as sketches. So we divide the dataset into two parts, into seen and unseen dataset, and the protocol which we follow is we want to just train the network on the seen classes, and we will test our algorithm on completely unseen classes. So this is the protocol of Zeroshot Learning. So why do we need Zeroshot Learning? So as we know that it is necessary to collect as many sample of data as possible for object classes. Now there will exist a lot of classes where we will get sufficient amount of data, but there will also exist some cases where we are not so lucky and we might not find samples for training for that class. So in such cases so why sketch-based retrieval? So one common example is because for such cases where we do not have training samples, we can quickly draw a sketch and use that as a query for a sketch-based image retrieval. Secondly, even if we do not have the sample during the training phase, for Zeroshot Learning we can always have there can always arise a case where we get the sample during the testing phase. And in such a case, if we train the model in a robust way, then even if we have not trained the framework for that particular class, during the testing time our method will still be able to classify it properly. So for that we actually need some kind of a semantic or an attribute information of the unseen classes for whom we are not being able to provide with image samples. So this is just an example where it's a Ilipika which was seen last summer in China's Tian Shan mountains. It's an example of an animal which is so rare that we cannot provide sufficient training class samples. But it might happen that our machine does encounter such a sample during the testing phase. So hence we need Zeroshot Learning. So this is the proposed overall pipeline of our proposed ZSCAMR network, which is the Zeroshot Cross-Modal Retrieval Network. So what we do is we have two different modalities inputs. So one is the sketch modality, which we call as the A, and the second is this is the image modality, and the second is the sketch modality, which we call as the modality B. Along with that we have the semantic information or the attribute information. So we basically try to extract the information using some kind of a pre-trained CNN network, which we have shown in experiments. We have tried different architectures for these pre-trained network, and we essentially want to project these features of A and B to a unified common space. So once we have a unified representation of features for both A and B, where we bring A and B closer to each other, then you can see that given a query of A, we can retrieve with the normal Euclidean distance from B, or given a query of B, we can retrieve from A. So for the unseen sample, to extend it to a Zeroshot framework, we need a semantic information. So we refer to this as semantic, SEM. We'll refer to image as IMG image and sketch as SKC in the next coming works. So to train our network, we basically design four different losses. So the first is a cross-modal latent loss. So here what we do is we try to, as I told you, that we try to reduce the distance between the image and some image and sketch. So we do it by projecting it to a common semantic space. So if we reduce the distance between image to semantic class and sketch to semantic class, we are automatically bringing image nearer to the sketch data set. So this is the first loss which we use in our architecture. The second is a cross-modal triplet loss. So we know the triplet loss, where we have a anchor image, we have a positive image which belongs to the same class and a negative image, which is an image of a different class. So in this case, we design a cross-modal triplet loss, wherein the anchor image is comes from the image dataset, and the positive image we take from the sketch, and the negative image also we take from the sketch dataset. Similarly, we also design image anchored triplets, where we get the anchor image as a sketch, and the positive and the negative class comes from the image dataset. So we have sketch and image anchored dataset. So this essentially helps in reducing the intra-class distances and increases the inter-class distances. Okay, also the cross-modal, the purpose of bringing the cross-modal latent loss is to bring closer the samples of image and sketch, and it also reduces the intra-class variance. Now, we also use a decoder loss basically. So this reduces the distribution gap between image and sketch. So the idea is, given an image instance, we reconstruct the corresponding sketch instance. So G is basically here a decoder function, where given the decoder of an image, which is supposed to be a sketch sample, we try to bring it near to a sketch sample. Similarly, the decoder of a sketch image, which we try to reconstruct it to as near to an image possible, that minus image. So the sum of these two gives us the decoder loss. So basically, essentially, the decoder loss helps us to achieve domain independence. Now last comes the classification loss. So this preserves the class information in the shared space and reduces the cross-modal intra-class variance. So this is the simple cross-entropy loss of image classes and cross-entropy loss of the sketch classes. So the overall objective function becomes the summation of the cross-modal difference loss, the reconstruction loss, the triplet loss, and the classification loss. Now for our experiments, we have used the Sketchy and the TubeBerlin dataset. The Sketchy has so many images and so many sketches, and we follow the common protocol used by all the classes, which is 100 training images, 100 training classes and 25 test classes. For the TubeBerlin, we use 220 classes as the train images and 30 classes as the test image. These are a few examples wherein given image query, we retrieve sketches. Given sketch, we retrieve images. So basically, our framework is robust to image-based sketch retrieval as well as sketch-based image retrieval. Typically, in existing literature, all the sketch-based image retrieval method do not allow us to have an image-to-sketch retrieval also. So, when we train our network just for sketch to image based retrieval and we compare it with the state of the art, so this is the ZSCMR network, the proposed ZSCMR network, and we can see that there is a clear increase in the map value in the Sketchy as well as TubeBerlin dataset. For the precision at 100, we are just a little behind the SAKE method, but this is compensated by the fact that our method also involves a cross-modal retrieval, which is sketch to image and image to sketch. Also, it can be extended since we project the features to a unified space. We also have a unified unimodal retrieval, which is the sketch to sketch retrieval and image to image retrieval. For both the values of for both the dataset Sketchy and TubeBerlin, we have shown the results. Now, we follow we perform some ablation study, wherein we show you the results of image. We add one by one each loss and see the effect of these loss. So basically, this is the total model. This is the total loss except the latent loss. So we can see that the latent loss actually contributes a lot to actually help in bringing the modalities closer. Without the latent loss, the performance of our model falls down considerably. This is the cross entropy loss. Again, without the cross entropy loss from the total loss function, the model performance falls down very much. However, without the triplet and the triplet loss and the decoder loss helps in achieving the extra boost over the other methods. So it does help in getting the finer, better results. So we would like to conclude by saying that the main motive of our problem statement is to project different domain data into a common embedding discriminative space. The model has been extended for a zero-shot architecture. It's a simple encoder decoder based architecture in place of a generative framework, which most of the existing architecture works are there. The proposed framework shows a significant boost to the current state of the art in zero-shot sketch-based image retrieval. Additionally, it also allows image-based sketch retrieval, which is the IBSR, and unimodal data retrieval. Thank you.